you lose the point of science, the joy of science and in inventing, in my opinion, you know.
Should they get a PhD? Or should they...
I mean, look.
What do you think?
Looking at the two of us, probably don't follow mine.
Why?
Follow your way. Turn them against each other, you know. So you use electrons to do this.
Okay.
We have the best inventors in the world, like 2,000 years ago. But let's not go back to the last 300 years of Greek history right now. Yeah, I mean, go like 300 years ago and tell to someone we're gonna have like phones, you know, that we're gonna have like
like video chatting and everything. The internet.
Yeah.
This is space. Welcome to an episode on the Estelle Ingenuity podcast. I'm Stephen Estelle, engineer, CEO, and founder of Estelle Ingenuity. In our episodes, we dive into different experiences from people who specialize in technology, entrepreneurship, and other necessary elements that will help you reach your full potential in these fields. We focus in on innovative devices that will be changing our society, stories from entrepreneurs and how they maneuver through the business landscape, and how these new technologies are being used in businesses to bring value to the world. From these stories, if you are inspired to develop your own inventions and prototypes, and you want to see your innovative ideas flourish, reach out to us at estelleingenuity.com for your prototyping needs so together we can begin creating the new devices of the future. With that being said, enjoy the show, follow and subscribe to Estelle Ingenuity Podcast, and relish the wisdom from the topic you hear today. So today we're here on another episode of the Estelle Ingenuity Podcast, and I actually have my good friend and colleague here today who actually has been around since actually quite literally the filing of my company. And I think that's actually very special because I remember talking to him about, hey, you know, I think I'm actually going to do it. You know, I'm going to get my business cards. I'm going to start a website and I'm going to do it. And so it's actually kind of nice to have you here. So this is Theo. Welcome, Theo. And for the podcast, give us a good introduction of who you are, where you're from, and everything that you like to do.
Absolutely. Thanks, man. Thanks for the nice introduction. And just in the same context, I just want to say that how I've told you so many times that you're so much inspirational to me with what you're doing, right? Because
I appreciate it.
We've been talking about this from the beginning, but I feel like sometimes I'm like only words, you know. And
you gotta start your own company.
And then you do like, and you're like, hey, it's so simple, man. It's so simple. Just go ahead, man. It's like, damn, yeah, it's just simple, you know. It's just like you said, allocate time and just do it. So yeah. Yeah, thanks. Like, I'm originally from Greece, and
okay. Where in Greece, out of curiosity?
Well, my hometown is called Katerini. It's in the north part of Greece, close to Mountain Olympus. That's like
okay. To you that sounds normal, but
yeah,
close to Mount Olympus.
I mean, I've been seeing the whole mountain from my balcony, you know. So I was like,
look at you. Okay, that's actually pretty cool.
Yeah, it's cool. I mean, it's like a small town, nothing like maybe 40,000 people. You know, that's the population. Good nature. So I grew up there, and then I went to the university in Thessaloniki. That's maybe like 50 minutes drive.
Yeah.
My hometown has like Aristotle University of Thessaloniki there, one of the oldest, let's say, universities.
Aristotle University.
Yeah, pretty old.
It's a big name, though.
Yeah. And I studied physics there. It's like a 4-year cycle, so I also did kind of integrated sort of thesis in the end. It was on more like nanotechnologies and material science, like some solar cells, you know, organic LEDs, these flexible electronics, as they call them.
Okay.
And so I find out about the place here, you know, and I just came to start to do my PhD in.
So then, I ask this to a lot of people. Why did you choose that field of study? Like, why?
The field of study. Well, it's interesting. I mean, as a kid, you know, I can't think of any moment that I wasn't fascinated with physics.
Like anything particularly about physics, or just
space? You know, I was like
okay.
any kid.
Yeah.
So even in my first year of undergrad, I was like, oh, space, astrophysics, this, that.
Are you a fan of Neil deGrasse Tyson?
Yeah, for sure. The guy's incredible.
Yeah, okay.
And so fun. I enjoy him so much.
Yeah, shout out to him.
yeah, absolutely. And you know, that was the biggest thing, you know. But going through the courses, I was also fascinated with the nano stuff, you know, because it's like the more we've been to to go to the outer space, like explore massive distances and sizes, exactly the same distance we've done like towards the nano world, right? Being able to fabricate nano stuff, like explore the atom, it's like I've been done so much work on this, and I'm still amazed by this,
Yeah. Which one seems harder? Exploring out there or exploring down to the...
Good question, man. I wish I could answer this. I'm not so good in either of this. I'm not so involved in either of this to really tell. I guess it's often come with their own challenges. In both of them, you need to be so specific, right? Down to, I don't know, micrometer probably.
Yeah.
Resolution or accuracy or whatever, like throwing something an orbit, around some planet or a moon is like crazy stuff. Like being able to fabricate with a crazy accuracy nanostructures or nanoparticles is also
right.
So,
was there anything particularly about space? Like, was it like black holes? Was it just like aliens? Was it about, I don't know, dark matter? What, anything?
Yeah, exactly. So actually at some point I realized that it was more like the poetic way, like the romantic way that space hides. I was fascinated with all of them. I can't tell, like I remember the first images of people on the moon, like people on the ISS. Actually, when I was 16, my school organized a direct communication with the ISS, the
Really?
International Space Station. So they have this program, because
I never heard
you
this.
you have to time it when they just come just above you.
Yeah.
And then you just have like a CB, like a
walkie-talkie
sort of, and you talk with this. And we actually asked them questions, and they were replying back like, and it was like a massive event. It was like such an important thing.
Really? I didn't know they do that.
Yeah. And I was like, man, we're talking with people out there,
Yeah.
And at that time in Greece, there were only 3 schools that managed to do this, And that was thanks to my teacher at that time, my physics teacher, obviously in high school, that he put a lot of effort and energy on this.
Interesting.
Yeah, so all of this, even today, I'm most interested in the tech science, more than the scientific is a thing, but space and all this hide a lot of mathematics.
Yeah.
But I kind of find them boring. But the tech part, like to have like space buses, to have like all the stuff up there, the satellites. That's what fascinates me. So I guess more like on the technological part of space.
Okay, no, I think that's the fun part too. Just as like an engineer myself. Yeah. So I'm curious actually, because I'm really interested in space because I always think about how like black holes and how if we could like control a black hole, or I know there's like talks about making one. And have you seen Interstellar?
Yeah.
Okay. Just making sure. Yeah, just making sure. I'm about to say if you didn't, I would have been very surprised.
I thought you were going to go there.
Yeah. Clearly, we gotta go. But so I wanted to ask, based off Interstellar and like how they kind of displayed the black hole, and this guy was just kind of like, I don't want to give a spoiler, but this guy was just kind of stuck in this. I can't even imagine. He was stuck between space and time or something like that.
Some like multi-dimensional space.
Right. Can you imagine if humans can, I guess, control that, and what we can possibly do? Like, I guess wormholes specifically, about traveling.
Yeah. Well, that's an interesting, because I've been giving it a thought after that movie, because it's like crazy movie.
Yeah, it's fantastic.
Yeah, the thing is, I don't know if, like the way we are biologically now, our body could could go through something like this, like a travel through a wormhole, for example, and survive. I mean, I don't see how this would be possible, honestly. That would be that goes more into biological function of our bodies, but that's what I think would be the main problem there. Technologically,
you need to send like a box through it, like a note in a bottle.
Ah, okay. I mean, why not, man? Why not? Again, I don't want to be too philosophical in this, but
yeah.
I mean, go like 300 years ago and tell to someone that they're gonna have like phones, or that they're gonna have like
video chatting and everything. The internet, just this space that has all this information.
Yeah. What would they say, right? I mean, they probably would say impossible. with technology that they had at that time, barely using tools for agriculture, right? So nowadays that we've seen what science and technology is capable for,
right?
Why not? Yeah.
Okay. Yeah, that's.
I don't see how this will be possible scientifically, technologically. I don't have the knowledge to put in this context, but yeah, I think it will be possible. Honestly, yeah.
I think I saw somewhere about that they were able to transfer something through a wormhole.
Really?
Yeah, I forgot what it was. I don't want to say if it was like an animal or if it was just like a small particle, but I think they said they were able to move. It was a very small distance.
They actually did it,
and they were able to move something over a small distance. Yeah, I'll have to look into that more details. But I do remember seeing something like that, and it was probably something so small that it was insignificant. I actually want to say it was like a fruit, but anyways, I guess the reason why that kind of catches my attention is because if we go down this path of making wormholes possible, I think it would make a lot of things obsolete if accessible to everybody, but it would also connect the world in a totally different place. Because potentially, quite literally, you can travel anywhere easily. And I think that would just almost make us maybe world citizens. Hopefully, thinking optimistically.
Yeah, I mean, listen to this, just I'm scared and excited at the same time, what could happen.
Yeah.
It's always the problem in science, that what forces do we release sometimes, we open Pandora's box.
Right.
And
it's
then
like the internet.
We're not sure exactly how to control it, so
it's gonna be sending cat videos over wormholes.
Yeah. But hey, look, I mean, something as simple as a electronic chip, for example, right? And it's found so many applications like phones, watches, computers, electric cars, anything, even I don't know, electric kitchens. Something so simple, right? It's found so many applications. Imagine something like being able to utilize and control wormholes. What would
I wonder if he'll get rid of cars, planes.
I hope so.
Maybe. So no, that'd be interesting. So then let's get into the meat of the conversation.
Yeah.
So, of course, to do amazing things with wormholes, you need, of course, the powerful technology behind it to support it. And earlier we were talking about how you have a big focus in quantum technology, which is something that I'm still not 100% familiar with, because quantum I feel like whenever I hear the word quantum, it's very intimidating. Yeah, it's just one of those things.
I don't know if you know what Feynman said. One sure for quantum mechanics is sure that nobody knows quantum mechanics. Nobody understands quantum mechanics.
Okay. So, given your interest in quantum, what's your take on it? What do you know? Just let me have it. What's your take on quantum and everything about it?
Yeah, well, first of all, that's a massive field.
Okay.
Honestly. It's a lot of things. And I mean, scientifically might be quite concise, let's say, but experimentally and from the technological part, there's so many approaches that try to approach this field. I'm doing experimental work, and in one of these very small part of quantum dots.
Okay,
that's the thing. All this hype now for the quantum tech comes actually again from the tools that we're able to use right now. Right, we are able. I told you before, that I was always fascinated by the technology and the tools that we actually have in our possession to do things.
Okay.
and all this experimental stuff starting becoming possible from theory to experiment to the lab, because of we're able to nanofabricate something. I don't know if you know the smallest. The problem with why quantum tech starts happening. We need more powerful chips.
Okay.
Like electric chips. Not electric chips. Electric chips are reaching a limit. We need photonic chips.
Photonic chips.
I believe IBM has the record for the smallest transistor, which is 7 nanometers.
So, Is there a simplified way of explaining what a transistor is?
Well, transistor is like a gate, let's say. It's like it's like a tap of water. There's one side the water is coming in, one side the water is coming out, and then you have also a way from the top to control the.
So it's just like a switch, like an on.
It's like a sophisticated switch and very high speed, high frequency anyway. That's why it's called. It's used for high frequency electronics. It's basically a way to very fast make changes. And that's what you use to send signals. Electric signals, for example, in the phones or in the computers, or the basis of all electronic stuff is electric signals. So everything. Do you know how many transistors a phone like this has?
I can't even imagine.
Yeah, it has about 500 billion transistors.
Really?
500 billion transistors.
In an iPhone?
In an iPhone, in a normal phone, Like, it's like 500 billion transistors.
Really?
It's insane, absolutely. Considering CPU, GPU, graphics card, and then RAM, and then all this space, all of them are using transistors.
So, okay. Oh, no, I'm trying to wrap my head around that. So, if an iPhone has that many transistors, and they're all just allowing you to redirect signals, correct?
Yeah,
or
yeah.
switching off and on. Now, if we go into the photon chips, does that allow us to use more transistors or faster transistors?
It allows us, first of all, to shrink the size. Because, like I said, the record right now is the 7 nanometers from IBM. And
that's already really small.
It's very small, right? We're a bit picky.
Yeah. Like, well, do you really need to go any smaller?
Yeah.
Okay.
You need, when you see
7 nanometers.
Yeah, when you see like what kind of problems computers try to solve, it's like I remember my first computer in 2000. I was like, wow, internet.
Right. AOL.
3 gigabit PS. Wow.
Yeah.
That's exactly it. And, hey, why would I need faster? Even nowadays. And then I'm running a simulation. Simple electromagnetic simulation. It takes me like 2 days to finish.
A 2-day simulation?
Yeah, easily, and it's not even the heaviest. I know groups that run like for weeks simulations.
Okay. So to do the simulation, things of that.
If you simulate the electromagnetic response, it's like you have to create a super fine mesh of the structure, and like. Anyway, I don't want to get there because I don't like the topic, and I've been working on this my PhD and I hate it.
Okay.
But anyway, we need So the photonic. There's a couple of things. First of all, electrons travel in, let's say, electric wires, right? So there is a lot of resistance and a lot of loss in this because of friction. Photons will not have this because photons, they don't usually interact with anything in there.
Okay.
So it's on like losses. It's second on size. Obviously, that's going to be the challenging part, And that's the problem. That's where quantum comes, because when you shrink something in such a small space, like below, usually around 10 nanometers, which is like the
10 nanometers. How? I'm trying to even imagine what does that even look like.
Well, it's like imagine, take 1 meter, which is approximately, if you just can open your hands about this.
Okay.
And then split it by 1 million times.
1 million. Okay.
Yeah. So that's gonna be the 1 nanometer. So you take 10 of this.
10 of those.
10 of this nano. 10 of this nano.
So like 100,000. Sheesh. What is that? Yeah. Smaller than like the tip of a pen, wouldn't it? You think?
Pin? What kind?
Like a writing pencil or like.
By a lot.
Oh my god.
By a lot, yeah.
So
by almost like 100,000 times.
So
no, let's not go.
Whoa, that's like blowing my mind. Like, how do you even fabricate something so small? You said you have like nano fabrication.
I have the photos here of you use how can I put this?
It's like I don't start it.
you turn them against each other, So you use electrons to do this.
Okay.
We have couple of machines, in our university, in our labs here that and it's a pretty common machine. I would say most universities have them, that you can use beam of electrons. You have like a gun of electrons, and you shoot electrons, and then so these electrons interact with whatever is in front of them, and then you can collect the scattering electrons, and then reconstruct the image, and then you can also use these electrons as bullets to destroy a target, with such a high accuracy and make a shape or whatever you want.
Okay.
In this like around 10 nanometers, that's it.
So what do you think if we have just so I say it correctly, it's like photon power chips, or what's the correct?
Yeah,
Photon,
photon sources, I guess.
photon sources.
Yeah.
So how would a photon sourced, let's say, iPhone be different than maybe our current iPhones? It would just be the computing powers of like.
Yeah, there would be, like I said, for losses, size and
So the size.
and speed. And speed, because obviously there's the light, the photon travels with the speed of light.
Gotcha.
And the electrons travel with about, I think, 100 or 1,000 orders of magnitude, like lower speeds.
Wow.
So we need basically faster, we need more powerful, and we need like a more smaller stuff to put in this way. That's why there's all the attention is there.
So could this technology also be used for like telecommunication over long distance in space?
Yeah, absolutely. I mean, that's why also the 5G is introduced in that case, because the 5G basically, I think it has to do with the IoT, the Internet of Things, that they want to have everything online.
Okay.
And have super fast speeds. The 5G, basically the Gs, the more the Gs increase, like from 3G, 4G, 5G, it gives you it shrinks basically the bandwidth that you can use, but it gives you more speed in the sense of the interaction. Everything has a lag time. When I send a signal here, it won't go a signal here immediately. It takes some time.
Yeah.
So it's all about minimizing this time here. For example, if you want like self-driving cars, that you're gonna go into your car and take me there, and then it has to communicate with satellites and internet, and then see the traffic, avoid things, and so on. You need speed. You need
now I get it. Now I get it. Okay.
Yeah.
So if we continue to improve on this like quantum technology and can improve the speed, things such as like, what do you think?
Yeah, sorry, that's a bit different. I'm sorry if I confused you. The quantum stuff goes towards computers.
Okay.
I throw in the 5G, which is a different one.
Okay.
But it's all in the race of efficiency, speed, and cost. Basically, that's everything is about this. The quantum tech is about computers, about creating more powerful computers. Like I said, like if I run a simulation with a computer today, in 2 days, with a quantum computer, I might be able to run it in 5 seconds. That's the order of magnitude. That's the order of magnitude, that we're talking about. Yeah, and then we can increase the complexity, because already in physics and in biology, we make so many approximations to solve something, because otherwise the simulations will take like weeks, and then the computer will crash, and then you will not have anything. So you have to compromise on something. I mean, I somewhere read something about even simulating the evolution of cancer in the human body with quantum computers. Can you imagine this? I don't know. It will give us such a power. It will make us understand.
So that's what they're doing, or that's what they want to do?
That's what they want to do. Yeah. The thing is, I'm talking all about photon sources, but obviously it's still very young technology, and there's so many problems that need to be solved. It's not so stable. Usually most of the photon sources of the previous 10, 20 years, it needs like ultra high vacuum and ultra cold temperatures. Which means that you won't be able to use your phone like this, because you can. So there are a lot of challenges, obviously, but all this quantum tech approach is the direction of how can we make single photon sources, like sources that send like one photon at a time, and be able to control this, and be able to receive this and detect it and translate it. And there are different approaches on this. One of these is the quantum dots that I'm working on, for example.
So quantum dots was...
Quantum dots is like I suppose that semiconductors, for example, everything in our life is like semiconductors. Silicon is the king of the semiconductors, that is like everywhere, basically, in all electronics, So semiconductors have they're sort of artificial also. There's, in some sense, engineered, the material engineering stuff, that you create an energy gap, with which gives you, the ability to control the light, emission light.
Like how much you want to be conductive through.
Conductive, What light, like for example, not these lights, but like certain lights, for example, like LEDs. The LEDs lights have control. You want blue light, red light, or white light, whatever. Semiconductors, okay? But now what happens when you take the semiconductor and you fabricate it in the nanoscale, as I said, in like less than 10 nanometers. Then you create an effect that is called quantum confinement.
Confinement.
All the energy levels, there's like continuous energy levels, they just become discrete, Like imagine, I don't know, I have like an idea of like having sort of like a bunch of paper on your hands, and then you squeeze them, and then you kind of create gaps in between. Can you get this?
Like, just like in like PCB boards, printed circuit boards, they have like vias. They're pretty much just like tunnels that go between the layers. Is that what you're talking about? Like a hole that goes between the different layers?
No. No. That's in the sense of the. No. It's not a physical. You cannot physically see this. What I'm saying is like the energy levels.
Oh, okay.
The energy levels. I told you that you create the conduction band that is like a continuous, in some sense, energy levels.
Okay.
And then the valence band also, And then when you squeeze this down to the nanometer, you force the electrons in these bands to not have like a continuous energy, but choose certain energy that they want to be.
Okay.
So that's a phenomenon called quantum confinement. Basically, you force the electron to be in a certain energy level, and then you also force it to only be able to move in certain energy levels.
Okay.
So that's basically a quantum dot. It's like a artificial molecule, even sometimes they call it, artificial atoms, consisting of these semiconductor nanocrystals. That because of their small size and small confinement in a small space, you create these energy levels that exhibit certain properties, such as emit. When I'm saying single photon emission, it means that it emits one photon at a time.
Okay.
Like these lights emit a lot of photons at a time, right?
Right.
But in order to go into the quantum technologies, we need to have one photon at a time, and then do something with this, and then take another one. And
so, like, when you say like emitting one photon at a time and doing something with it, what exactly do you mean? Like, what are you doing with it?
Yeah. So.
Like just measuring it or like testing?
Yeah. I'll tell you in a second. Like, the simplest. I think we kind of learned this already from school, maybe, that we have any semiconductor has like electrons on the below low energy level. If you excite it, then it goes up to the conduction level and it stays there for some time, right? But then for the quantum dot, if you have one electron up here, you cannot excite another. It's going to be only one excited electron up here.
Okay.
So that means when it comes down, there's going to be only one photon coming out. The recombination of charges back to the valence band creates an emission of photon. If you have like a big semiconductor, then you can have like electrons and photons from everywhere going through. But if you have a confinement, then you have only one photon going out.
Okay.
So what are you going to do with this photon?
Yeah.
It's insane, and it's so hard even for me to put it in words and to understand it, but basically you can split the photon.
Okay.
And recombine it again. And that's the
what does that do?
That's a photon interference. It's like an interferometry, I guess Heisenberg's uncertainty, and it also goes to Schrodinger's cat box, let's say this experiment.
Like the whole like is it there or not kind of thing? Or?
Yeah, so the idea is that you send one electron into a crossroad. Okay? And it has to choose which side it's gonna go.
Okay.
And then you recombine it on the other side,
Right.
And the thing is that you don't know which path your photon went, but you can calculate the probabilities.
Okay.
Like might be sheer, depending on the conditions,
I've heard of this before.
Yeah. But you don't know, and you cannot know unless you put your finger in there and measure it. In which case, you destroy everything. Yeah. So it seems to me that we will never know, And you can have like one photon splitting and then interacting with itself. That was the young slit experiment with the diffraction pattern. I don't know if you remember that if you have like two slits and you send like two bullets, then the bullets are just gonna pass through the slits, and you're gonna have two lines behind the target, right? From the bullets that pass through the slits. Right? If you send water, then the water will pass through the two slits, but then it will start interacting. That's the interference. And then you get an interference pattern on the target. I don't know if you remember, like, that goes like a wave, and then in the center it goes like very, very like high.
I've seen some videos talking about that.
Yeah. It's called the interference pattern anyway. You can do this with light. You can send multiple photons and again take the interference pattern. But here's the weird. You can also do it with one photon.
And it interferes with itself?
Yeah, it sort of splits, it interferes with itself, and then you get the interference pattern on the target behind, which is insane. It interferes with itself, exactly.
What Theo, what does that mean?
Man, I don't know.
What does that mean?
Go read some proverbs.
What does that even mean?
I'm gonna give some food for thought here. Yeah, I don't know. It means that we don't know anything about light. That's what it means.
Interesting.
Yeah, and it's not theory. That has experimentally been observed.
But like,
there's experimental observation.
But kind of going back to what you said, the observation changes it. So like, are you actually observing what?
Well, but you only view the end. You don't change matter. Like, you only view the end of this. Yeah.
Okay. Jeez. Yeah, I can't.
And so
this is why quantum always intimidates.
Yeah.
Because we think it's there because we measured it, but then it's like, but the measurement changed it. But then it's like, I don't know. It seems like it's like two places in one time, kind of whole idea.
Totally, man, totally. And I hope I don't say any stupid things here, and I confuse the people who are gonna listen to this.
No,
and I don't. I feel like I feel uncomfortable talking about this, because I'm no expert, obviously.
Dude, you sound like an expert to me.
No, unfortunately. But it's insane, and we're able to control this. That's the thing, Like, go back to Heisenberg and Planck, and all these guys who contribute in Schrödinger, who contribute in this theory, and tell them that, hey, we observed it.
That we did.
We saw it. You were right, man.
And then you got like people like, oh, what does that even mean?
Yeah.
I thought it was interesting when you mentioned much earlier when you're going to simulations and why it is important to have powerful computers. And that idea that you mentioned about potentially simulating like the cancer evolution of a person. And I guess, like, I understood why simulations were important because, of course, you could test things out. But I guess I always thought about simple simulations, I guess, like, let's simulate maybe traffic and then we can automate a car. But yeah, trying to simulate like a cancer evolution through a human body would, of course, be a lot of possibilities and a lot to look into. And if we were able to achieve that with this technology, quantum tech, I mean, potentially maybe quantum tech is actually a first step to reducing cancer potentially. Maybe, I don't know. Maybe it could be like I don't know, these powerful computers. I guess I never really understood, like, why do we need to get faster? Even though I do know why, but, like, what is the application for faster computers?
Yeah, like I said, like, I had the same idea.
Yeah.
And that's what I also, like, come on, let's focus on something else, But then, when you come across the problem, like, damn it, I wish I could do this faster.
Right.
And sometimes, and it's also sometimes science is not why, but sometimes science is like, why not?
Yeah, and that's why I like it. That is why I like it. Yes.
Yeah. The things get a bit more complicated, with having to write grants, having your position dependent on the papers and things like this, you lose the point of science, the joy of science and in inventing, in my opinion,
Because of the grant process?
Because of the process of how stressful it is and the deadlines and everything. And, I finished my PhD now, and looking back, I was like, damn, I wish I could have done more things, and like, just go down to the lab and do stuff for my curiosity. But is it really possible,
Did you have the time, or did you just...
That's the thing, yeah. I mean, if you don't have, like, your results to graduate at the first place, and then when you struggle for this, when you're stressed about your PI, like pushing proposal, exams, you have to go to a conference and show them something, that it's not, it's something that makes sense, it's like so many things. It's not so possible, when you come to a place and you have like 5 years, 6 years of funding and then go home.
That was the end of an episode of the Estelle Ingenuity podcast. Hope you learned something new and innovative and were left inspired to go create and invent new ideas for the betterment of society. Make sure to follow and subscribe to the Estelle Ingenuity podcast on Spotify, Apple Podcasts, and YouTube for more stories and experiences from people in the field and to hear about new up-and-coming technology. Thank you for listening and see you in the next podcast episode.